All right, so we are going to today go over how the second derivative will give us some information about key features of the function, including concavity and points of inflection, and even the local extrema in some cases. Okay, so we're going to look at sketching f of x equals x squared minus 2x plus 4. You can use an online graphing calculator, and Desmos is really one of the best ones. So here is my f of x equals, here we go. F of x equals x squared minus 2x plus 4. So you can just give a quick sketch of that on your own sheets. Let me just zoom in a little bit for the scale. There we go. Just a little rough sketch is fine. And then the nice thing about Desmos is if you do put in f of x equals, and then you show f prime equals, it'll just give you the graph right away. You don't have to type in the equation. Okay, so that is the first derivative. And if you do the same thing for the second derivative, f prime prime, this time it won't show you, but it'll tell you the value is y equals 2, so you can just put in y equals 2 manually. So just draw a quick sketch of those three functions on your page, and it looks like so. And just in case none of that worked, the way that I got these sketches, I used desmos.com/calculator. Okay, so now we're going to answer some questions about the function. Just looking at this table going across, the function when x is less than 1 is increasing, has a local max, has a local min, or is decreasing. I think the answer should be decreasing. At x equals 1, we have a local minimum. And then when x is greater than 1, we can see that the function is increasing. So that's all based on my f of x graph. Now let's answer some questions about this first derivative. That's my graph in blue. So I can see when x is less than 1, the first derivative is negative. When x is equal to 1, the first derivative is 0. Then f prime is greater than 1, or when x is greater than 1, f prime is positive. And I can also answer some questions about the second derivative, which is my graph in pink. And the equations are actually given to you on the side here. Okay. So the second derivative is always positive. Doesn't change. It's a constant, y equals 2. And overall, we can conclude that the function f of x is always going to be concave up on all of its XER intervals. So if you move on to the next page, we're just going to repeat this investigation using a cubic function next. Again, I would recommend that you use desmos.com/calculator to graph this function. Here it is. So you can sketch this function as well as its first derivative and its second derivative on your page 2. So take a minute to do that. Press pause if you need to. So going back to the lesson page, we have the sketches of f of x, f prime, and then f double prime. And again, we're going to answer some questions about each of them. So looking at the original function, f of x, when x is less than -1, we see that the function is increasing. At x equals -1, we see there's a local maximum. between -1 and +1, the function is decreasing. At x equals 1, there's none of these important points. It's still decreasing. And from 1 to 3, the function is still decreasing. At x equals 3, we have a local minimum. And then when x is greater than 3, the function continues to increase. So that was looking at the original function f of x. Now looking at the first derivative, which has an equation of 3x squared minus 6x minus 9, and it's the graph in blue. When x is less than -1, we see that the function is positive. When x is equal to -1, it's 0. From -1 to 3, it's always negative. When x is equal to 3, the derivative is 0, and then from 3 onwards, the derivative is positive. Now, the second derivative, this line in pink, when x is less than -1, the function is negative. In fact, it's negative all the way up to x equals 1. So at x equals 1, the second derivative rather, is 0. Then, when x is greater than 1, the second derivative is positive. Looking at this function, we see that until x is equal to 1, the function is concave down. And then at x equals 1, we have a point of inflection. And then the rest of the way, when x is greater than 1, the function is concave up. So let's move on to the next page. So we're going to make some conclusions based on the first 2 pages, the investigations that we just completed. The concavity test is as follows. On any interval, a function will be concave up if the second derivative of the function, so on the previous pages, our f prime prime, second derivative of the function, is positive. If you look back at pages 1 and 2, anytime we had f prime prime being positive, the function was concave up. And then a function would be concave down if the second derivative of the function is negative. So if we have here, for example, a simple parabola, clearly it's concave up, and that's because the second derivative is always going to be positive. And then if we have a parabola opening downwards, in this case, then the second derivative will always be negative. And that's why the function is concave down. Another way to see this is that all of the tangent line slopes can be drawn below the curve. And as you can see, they're going from negative slopes to 0 at the minimum, and then they're increasing to positive. So when this happens, our function is concave up, and the second derivative is positive. And then let's do the same thing for the concave down function. We can see that the slopes of the tangents start out positive, and then at the local maximum, it will be 0. And then the slopes will turn into negatives. So when we say that the second derivative is positive, it's really because the slopes of the tangents are increasing from negative values to 0 to positive. So this really means that the first derivative is increasing. And that's why the function is concave up. That's why the second derivative is positive. And then when the slopes of the tangents are decreasing, then the function is concave down because this means that the first derivative is decreasing. And therefore, the second derivative is negative. So there's that connection. Again, if you go back to investigations 1 and 2, you'll see that the function f has a point of inflection at p if f double prime of p equals 0, or if f double prime p does not exist, provided that p is in the domain of the function and the sign of the second derivative is different on either side of p. So if I give you a quick sketch of the function, maybe a cubic one, like so. Here, this is going to be our point of inflection at x equals p. So to the left of x equals p, our second derivative is going to be positive because, negative because the function is concave down. And then to the right of the point p, the second derivative is going to be positive, concave up. And at p, our second derivative is going to equal 0. And that's how we know we have a point of inflection. The sign of the second derivative changes from negative to positive. Okay? And another example here, when we said up here that the point of inflection can also occur when f double prime does not exist, but p is in the domain of the function. We're talking about, for example, when we have an infinite slope point. Okay? So here's point x equals p. Until this point, the function is concave up. So that means that f double prime is positive. And then to the right of that point, the function is concave down. So that means that the function's second derivative is negative. And at this point, we know that our first derivative does not exist, right? Because of the fact that we have an infinite slope point. If the first derivative does not exist at x equals p, then automatically we know that the second derivative will also not exist. So even though x equals p is in the domain of the original function, the second derivative does not exist. And on either side of p, the sign of the second derivative changes from positive to negative. So that's how we know that we have a point of inflection. POI. POI, remember, for curve sketching unit, does not stand for point of intersection. It stands for point of inflection. Now, for this last example here, the second derivative test, this is another test that will help us to determine where we have local extrema. So go back to your investigations on pages 1 and 2 and look at where the first derivative equals 0 and where the second derivative is positive. You should see that at such a point where the first derivative equals 0 but the second derivative is positive, we are going to have a local minimum at x equals c. And then if the first derivative is 0 and the second derivative is negative, then we're going to have a local maximum at x equals c. So let's take a look at why this works. Again, just using a parabola as a simple example. Our first derivative at this point, x equals c, is 0. the slope of the tangent line will be horizontal. But we can see that the entire function is concave up on its domain. So that means that f prime of c will be positive. Okay? So when these two conditions are met at the same time, at the same point, that means we have a local minimum at x equals c. And we can repeat this time with a point where f prime of c is equal to 0 and the second derivative is negative. So we have the function here concave down. This is concave up. Okay. So when the function is concave down and we have a critical point where f prime is equal to 0, that means that we will have a local maximum. So the second derivative test is very useful when it works because it's a little bit faster than creating the interval table or the number line for the first derivative to figure out your local maxes and mins. You can use the second derivative test. If it works, it's a little bit faster. Okay, so if we move on to the next page, we'll see that there is a condition for the second derivative test. We can't use the second derivative test if the second derivative itself is equal to 0. Okay, because in that case, there could be local extrema at x equals c, or there could be a point of inflection. So in order to figure out which one it is, you have to create an interval chart. And as it points out in the notes, okay, sometimes the second derivative might be a little bit too messy to calculate. For example, if you're starting with a rational function, so you might not always want to use the second derivative test. Okay, example 1, determine the concavity between the points indicated. So from points A to B, we can see that the graph is going to be concave down. And from B to C, the graph will be concave up. Okay. And then the graph will be, once again, concave down beyond C. So a function is said to be concave up on an interval if the function itself lies above all of its tangents. So if we were to graph some tangent lines from B to C, we can see that all of the tangents will lie below the curve, or the curve will lie above the tangent lines. And the graph is concave down from points A to B. That means that the tangent line lies above the curve, or the curve lies below the tangent line, however way you want to think about it. Same thing with point C and beyond. Just some definitions. Okay, so now let's go on to example 2. We want to find and classify all local extrema using the second derivative test for the function f of x equals 3x to the 4, etc., minus 16x cubed. Okay, so let's figure out f prime. It's going to be 12x cubed minus 48x squared plus 36x, and then the constant 2 will just become 0. So this is my first derivative. And in order to use the second derivative test, we need to figure out where the critical points are. So let's set this equal to 0 so that we can solve for x. You can factor out 12x easily. So it'll be x squared minus 4x plus 3. And this is a factorable trinomial, x minus 3, x minus 1. So we know that there are 3 critical points, 0, 3, and 1. So now we need to figure out the second derivative. That's going to be 36x squared minus 96x plus 36. So with this second derivative, we now need to plug in these critical points to see if the second derivative will be positive or negative. So for 0, 0, 0, 36 will be the answer for the second derivative. So because we know that the second derivative is, so f prime 0 is equal to 0, and f prime of 0 is positive, then according to the second derivative test, that means we will have a local minimum. Okay, let's repeat this for f prime prime of 3. So when you plug in 12 times, oh, sorry, not 12, 36, 3 squared minus 96 times 3 plus 36. Calculate. We end up with 72. So f prime 0 is equal to, or sorry, f prime of 3 is equal to 0. And the second derivative was again positive, so that means we have another local minimum. One last time, we have f prime prime at 1, 36 1 squared minus 96 times 1 plus 36. Calculate. And we get negative 24. So for this final answer, because f prime at 1 equals 0 and f prime prime of 1 is negative, that means we have a local maximum. Okay. So we're just going to give a quick sketch of this function. We know even from advanced functions, we have a quartic function, and the degree is 4, and we have positive end behavior, so it's going to go from quadrant 2 to quadrant 4. So we have at x equals 0, at x equals 3, and at x equals 1, we're going to have our local mins and maxes. So now we can say that we're going to have minimum, a maximum, and minimum. And then we already determined that the end behavior would be from quadrant 2 to quadrant 4. And this is going to be a very rough sketch because all I did was find the local minimums and maximums. If I wanted a more accurate sketch, I really would have to figure out the rest of well, basically I would have to figure out concavity, points of inflection, etc. Okay, but just for this question here. Okay, this is something along the lines of what the function would look like. And you can always just double check your answer using desmos.com. Okay, let's move on to the next page. Okay, last example, we want to determine where the graph of this polynomial function is concave up and where it's concave down, and then we're going to locate any points of inflection. So in order to do that, we're going to have to figure out, first of all, what the first derivative equals. So that's going to be 3x squared minus 6x plus 4. And then, because we want to know concavity and POIs, we're going to need to figure out now the second derivative. So it's going to be 6x minus 6. Okay, now we want to figure out where f prime prime is equal to 0, or where does it not exist? Okay, We can clearly see that this is a continuous function, so this criteria is not going to be met, but we should be able to figure out some x values where the second derivative equals 0. So we are going to now plug in 0 equals 6x minus 6. And then when we solve for x, we are going to get x equals 1. So now we should either create a number line or an interval table to determine whether the concavity will change from positive to negative, and then that will help us to figure out if we have a point of inflection. So we can clearly see that when we plug in a value less than 1 for x, that the second derivative is going to be negative, which means that the original function, f of x, will be concave down. And then when the second derivative is positive when x is greater than 1, that means that the original function will be concave up. So we can write, therefore, f of x is concave down when x is less than 1 and concave up when x is greater than 1. Okay? We know this because the sign changes at x equals 1 and the second derivative at x equals 1 is 0. So that means that we also have a point of inflection at 1, 2. And how did I get this 2? It's because I plugged in 1 for x in the original equation. So 1 cubed minus 3 times 1 squared plus 4 times 1. Okay. That's it. Just one more point. As we move on to doing or graphing a little bit more in detail, you will figure out that the graph of this function more accurately looks like this rather than this. And the reason why is because we would go back to the first derivative and look for any local extrema. Okay, so this would actually be the more accurate graph, and this one would be incorrect. So we'll figure that out more as we go along through this unit. That's it for this lesson. Thanks.